going to talk about lipids and membranes today. So, unlike some other families of organic compounds that we looked at, lipids are really classified based on the fact that they're water insoluble. So, they're water insoluble biochemical compounds. They're going to look a little bit different from each other. So, we're going to look at steroids. They're going to have like a ring structure versus a triglyceride, which is going to have a glycerol backbone and some fatty acids. So they're not always going to look exactly the same, but the one thing they have in common is that they're relatively insoluble in water. These are some uses of lipids that we may have seen before. Cell membranes, you probably have seen that double bilayer, phospholipid bilayer. These can also be used as energy storage in molecules, insulation, hormones. So insulation is in your fats. We're going to look at fats. Different classes of lipids will have fatty acids and waxes. Triglycerides, triglycerides are going to have a glycerol backbone with 3 fatty acids. We're going to have 2 types of phospholipids. Phospholipids are going to have some phosphorus in there, some phosphate, and then we separate them based on what type of backbone they have. Do you have a glycerol backbone? Do you have a sphingosine backbone? Glycolipids are going to have some sugars involved there. And then we'll look at steroids and eicosanoids. Those are kind of fun too. So the first part is just on fatty acids, like what is a fatty acid? It's a carboxylic acid, so here's our carboxyl group. We've seen this before. We've got a C double bond O with an OH. That's going to be the head group of the fatty acid, and then it's going to have a long tail, and this tail is going to be carbons and hydrogens. You can see you have lots of, CH3, CH2. This one doesn't have any double bonds in it, so this would be what we call a saturated fatty acid. It's going to be has each one of those carbons is saturated with hydrogen, taking on as many as it possibly can. Fatty acids are going to have between 12 and 20 carbons, and usually an even number of carbons. That's what we'll find with our fatty acids. So fatty because one side is going to be nonpolar, it's going to have this nonpolar tail, and then you have this slightly polar head group over here. So we said saturated fatty acids contain only single bonds. There's no double bonds in there, so this would be a saturated fatty acid. If you put one double bond in there, then it's called a monounsaturated. Mono for the one, unsaturated means there's a double bond. So this is one with one double bond. And then you can have more than one double bond. And if you do that, that's called a polyunsaturated. So poly means many, unsaturated means you have a double bond. So polyunsaturated fatty acid, you're going to have 2 or more double bonds in your structure. And that's going to affect a lot of things, the physical properties of these fatty acids. So if you just have a saturated fatty acid, this is going to be like a long chain. You can see down here what that looks like. We're going to have this long straight chain, these things, and you can just keep building on this. They're going to be able to pack really tightly together. There's going to be a lot of surface area overlap between those two. And the surface area, you think about that, it's like the glue that holds those molecules together. So if you can pack these really, really tightly together, there's going to be a lot of interactions there. It's going to take you more energy to separate them. So these are going to end up having, higher boiling points, higher melting points. Let's say that higher boiling point and melting point because they have stronger intermolecular forces. They'll have stronger intermolecular forces. So those are those are, in particular, we have London dispersion forces here. So those are the forces that hold those molecules together, intermolecular forces. And that's going to give them higher boiling points and melting points, all those sorts of things. So those are saturated. So saturated fatty acids have higher melting and boiling points. We said because they're hydrophobic tails. Those hydrocarbons can pack close together. They have higher London forces. So the longer the chain, the stronger your London forces are going to be. So the higher the molar mass, the greater the London forces, the higher the boiling point. As the number of carbons increases, yep, that's exactly what we're saying. So does the boiling point and the melting points. And then most saturated fatty acids, so most of the ones that don't have any double bonds in there, the ones that pack really tightly together, these guys over here, because they have higher melting points, they're going to tend to be solids at room temperature. Whereas if you have unsaturated fatty acids like this guy, see how it has a cis double bond in here. It forms like a little kink. You can't pack those as tightly. And so because they can't pack as tightly, they have lower or weaker intermolecular forces. And so they're going to have their boiling points are going to be not quite as high. Like it doesn't take as much energy to separate those. It's going to be easier to turn this from a solid to a liquid. So these will tend to be liquids at room temperature. So these guys are going to be liquids. These are going to be like your oils. A lot of oils will have um, unsaturated fats in them, but saturated fatty acids, that's going to be more like a solid at room temperature, so like lard. You can think that versus oil. So this would be like an oil over here, and we'll talk more about that in a second. Um, all right, so the saturated ones are going to pack tightly. The unsaturated ones are not going to pack tightly. So to answer this question, which fatty acid would you expect to have a higher melting point? So these are both saturated fatty acids. We don't see any double bonds drawn out there. This CO2H, this is just another way of writing a carboxylic acid. You're going to see that a bunch of different ways. You can see it as CO2H, COOH, or you can draw it out C double bond O with an OH. Any of those, they all represent the same thing. So we'll see this written a bunch of different ways. So because this one, we're not showing out any double bonds or anything, we're really just looking at the total number of carbons that we have here. And this is a shorthand way of writing this, CH3, CH2, 10. That just means that CH2 repeats itself 10 times. So instead of having to draw out this structure, we could just write a shorthand CH2, CH3, CH2, how many of those we have, and then a COOH or CO2H. So this is just a carboxylic acid that has 10, 11, 12 carbons. This guy has 12 carbons in it. This one is going to have, I have 16 CH2 groups, so I've got 16 carbons, 17, 18 carbons total over here. So because this guy has more carbons, he's also going to have more hydrogens because each one of those carbons is going to have 4 bonds. So each one of those carbons comes with all the hydrogens that it needs in order to satisfy its octet rule. So because this one has 18 carbons and the other one only has 12, the one with 18 is going to have a higher melting point. It's going to be harder to melt that. So it's going to have stronger intermolecular forces. So the more carbons you have, so the increased molar mass, here we go, increase carbon chain length, that's going to increase the boiling point and the melting point of this. So it'll have stronger intermolecular forces. Let's see, we have another question about boiling point. So which of the fatty acids below do you think would have the lowest boiling point? So like, what does that mean? A low boiling point? Low boiling point means you're going to have weaker, so lower the boiling point, you're going to have weaker intermolecular forces. They're not going to be packing as tightly together. So this is going to be one that maybe has a lot of kinks in it. So maybe you have more than one double bond. So saturated, that's going to have a pretty high boiling point, high melting point. This is going to have, it's going to pack really tightly. So this is when you're packing everything like that. So this is your long straight chains. Monounsaturated means you're going to have something like one like little kink in there. Polyunsaturated, you can have a bunch, right? Maybe it kinks that way and maybe it kinks this way, and then it's going to be kind of kinky. I don't know how you want to draw that one. But polyunsaturated, they're not going to be able to pack very tightly. So because of that, they're going to tend to have weaker intermolecular forces, which is going to give rise to a lower boiling point. So if you're comparing saturated versus unsaturated, the more unsaturated you are, the more double bonds you have, the weaker your intermolecular forces are going to be, and the lower your boiling or melting point will be. What else did we see? So carboxylic acid. So this is a carboxylic acid. Remember that functional group C double bond O with an OH. This one's pretty small. It's got two carbons in it. This is going to be pretty soluble in water because this guy is going to be able to form hydrogen bonds. The polar versus the nonpolar part of that molecule is the polarity. This thing is more polar than it is nonpolar. Now, as I start increasing this chain, so this guy has one methyl group, and then this one's going to have CH3, and then I've got 4 more carbons in there. Once I start increasing this chain of carbons, the solubility is going to start to go down. And so this one I can only dissolve maybe 1 gram in 100 mils. This one's miscible, which means it's going to dissolve in all proportions. So no matter how much water or acetic acid I have, that's going to be soluble. And then once I get up over here to like where I have 12 CH2 groups in here, plus the one that's in the carboxylic acid and the one that I'm starting with, the longer this chain gets, the more insoluble in water it becomes. And so this is, we call this one a fatty acid. So once it's like not dissolving in water anymore, we consider it a fatty acid. So that tends to happen around, when you have 12 to 20 carbons in your chain, then that's no longer going to be very soluble. So one thing that you can do to make this a little bit more soluble is to look at this head group. So again, this is our polar head group, and then that's our nonpolar tail. If we can make this polar head group actually ionic, if we could put this under, react this, it's an acid, right? This is a carboxylic acid. If I react that with a base, I have a quick little acid-base reaction happening here, and I can turn this carboxylic acid into its conjugate base, and that conjugate base will be ionic. So this is what we're doing here. We're turning this into an ion, and ions are much more soluble in water. So if you form the conjugate base of that carboxylic acid, now you're going to increase the solubility. So one way to make this more soluble, and again, soluble just means it's dissolving in water. One way to do that is to react it with a base, and the base will basically make this ionic, and then now I have an ionic head group, which is going to be more soluble in water. So this is showing like a long fatty acid chain. So whenever you see carbons and hydrogens, just carbons and hydrogens, that's going to be not nonpolar. That's going to be like a fat. That's a fatty acid, not polar. It's not going to be soluble in water. And then over here you have this tiny polar head group, which will be soluble in water. But if you turn it into an ion, see, instead of having this carboxylic acid, now I have this carboxylate ion. This sodium is there to just balance the charge. That you could put sodium there, you could put potassium there, depending on what base you're reacting it with. There's nothing really special about that sodium. Any of those group 1 metals, we'll see this happening with. It's really just the fact that I'm taking this hydrogen off. When I do that, it becomes charged, it becomes ionic, and then it becomes more soluble in water. Once we do that, we call this amphipathic. Amphi means both. Pathic is talking about whether it likes water or it doesn't like water. So this one means we have a hydrophilic section, we have a hydrophobic section. The hydrophilic part is going to like water. That's going to be your polar head group. That's the hydrophilic. Oops, let's see, hydro. And then the hydrophobic section is going to be all of this over here. That'll still be hydrophobic. That part's hydrophobic. Now, this is going to be pH dependent. So we said that this is an acid, right? This is a carboxylic acid. Carboxylic acids under acidic pHs, so at low pHs, the acid form of this is going to dominate. At a higher pH, at a basic pH, then you're going to find the carboxylate anion is going to dominate. The conjugate base of that will be what's in our solution. So in the human body, the physiological pH in our blood is like it's around neutral. It's a little bit slightly basic, but mostly kind of neutral. So under those conditions, these fatty acids are going to be in their carboxylate, so in their basic form, which is great because it makes it more soluble. So what's one benefit of reacting a fatty acid with sodium hydroxide? That's a base, again, making that base. It's going to increase the solubility. So the whole purpose of doing this is just to increase the solubility. Increase the solubility. That's why we do that. All right. Let's see. One more thing that we want to talk about in this chapter is looking at omega-3 fatty acids. You may have seen those, maybe you've seen them in the news. Maybe you take fish oil supplements and you've seen those on there, or you've heard about some of the benefits of taking omega-3 fatty acids. This is we'll go over how we name them. So it's a fatty acid, so it's going to have this long chain of carbons, and it's also going to have some double bonds in it. And so we're going to label where do we find those double bonds, and those are going to be that's where we get that omega designation. So this is the Greek letter omega. It's like a little W. Omega-3 fatty acids are something like this. So when we normally name carboxylic acids, we would start with this guy being this like carbon number 1. When you're using the omega designation, you're trying to figure out where the double bonds are, and you're going to start at the omega, the last. Omega is the last letter, I think, in the Greek alphabet. So we're going to start on the other end. So we're going to start over here and try to find the double bond. So this has a double bond on omega 1, 2, 3. So this would be an omega-3 fatty acid because the double bond starts at the omega-3 carbon. This is linoleic acid. These are some of the health benefits of eating foods that are rich in omega-3 fatty acids. So it's going to increase your good cholesterol, HDL levels. That's your good cholesterol. LDL is the bad cholesterol. So it makes this is going to increase your good cholesterol. It lowers your bad cholesterol as well as your triglyceride levels. And we'll talk about triglycerides in a second. It also decreases your blood pressure. And when you do that, that's going to lower the risk of heart disease. So all of these things are, benefits of eating foods that are rich in omega-3 fatty acids. It also decreases inflammation due to rheumatoid arthritis. Omega-3 fatty acids, where do you find those? These are essential nutrients, which means your body does not make them. You have to consume them in your diet in order to have them. You can find omega-3 fatty acids in some plant oils like flax, canola, and also fish, and fish oil supplements. So you'll see cold water fish like salmon and herring, and then if you look on a bottle of those fish oil, I can smell these fish oil supplements. If you look on the bottle of those, you'll see that they have these omega-3 fatty acids in there as well. So arachidonic acid is another type of omega fatty acid. So I know I can use the omega designation system because I've got these double bonds. I've got multiple double bonds here. And all we're trying to do is find which carbon is the first double bond on. So I'm going to start not on carbon 1. I'm going to start numbering my omega carbons all the way at the opposite end. So this is omega carbon 1. So we'll start counting on like the last carbon. 1, 2, 3, 4, 5, 6. So this guy is an omega-6 fatty acid because that first double bond starts on the omega-6 carbon. There we go. And our bodies require omega-6 fatty acids to remain healthy. But if you have too many of them, it can cause problems like inflammation. So you don't want to have inflammation. Omega-6 fatty acids are found in eggs and avocados, cashews, and many other vegetable oils. All right.